welcome to Impactful Innovation with Commercis, the podcast series that reveals how technology innovations are impacting our lives, our work, and the world around us. I'm David McClelland, and in this series so far, we've looked at some of the technologies right on the bleeding edge of innovation. And in today's show, we're going to explore the edge a little further. What is edge computing? Where does it fit alongside the data centers that we've already explored? And might a so-called brain on a chip be the ultimate edge computing device? Lots of questions, and the good news is that I'm joined today by guests who, well, I hope have a lot of answers for us, including joining me here in the studio, CEO for Commercis Technology and Intelligence, Vipul Narula. Vipul, thank you for joining us.
Thank you very much, David, for inviting me. Thank you.
Now, you've spent a few years in the industry, and we've seen different computing models kind of come and go. Obviously, we've explored data centers in some depth so far. Today, we're talking about edge computing. So what's the pitch, if you like, for the edge computing model? What does it give us above and beyond what the centralized data center model gives us?
And again, a very good question, David. Edge computing is all about data. When you look at data and the vast majority of data and the user cases around the data where data has been created, consumed, and where the idea is to make it as faster processing for the customer, that changes the equation. The user cases, the data, the compute power in your hand, millions of IoT devices creating that data, and that is where the edge compute takes effect. And how faster we can get that data, process it in the right framework, whether it's AI, non-AI, and create the right data framework for the customer, right kind of information for the customer in real time or in the time as it is appropriate for that industry.
Because I think expectations have changed, and me as a consumer, either as an individual or as a corporation doing financial transaction processing or whatever it is, my expectations of how quickly I feel I should be able to get to my data and do some processing have changed dramatically, even over the last few years. You know, what's acceptable to me has shrunk. I need my stuff, however big that stuff is, faster than ever before. Otherwise, I'm feeling impatient.
Absolutely. And it's not about just feeling impatient. People's life is at stake if you're not processing data fast enough. If the compute space is not next to the customer, where the data has been created, remember where the data has been created, whether it's the cloud, whether it's an enterprise side of things, or whether it is in a car.
Right. Hold that thought there, Vipul. Thank you very much indeed for kind of teasing us with the edge computing dream there. Earlier in this series, we heard from Duncan Clubb from Cambridge Management Consultants, who is an expert in designing and building data centers, but he also has a lot to say about designing and building for the edge.
So edge computing is about putting compute power much, much closer to where data is generated or used. There are typically three reasons for doing that. One is latency, where you need the processing to be very, very fast. And a good example of why you want to do that is in real-time control systems, right? So several years ago, industrial firms realized that they could make huge savings by improving production line efficiency, by monitoring what was going on using various types of devices and cameras, and then processing that data and making real-time changes to the industrial processes to improve efficiency, to reduce wastage, a whole load of different things. And, it's been extremely successful. And there'll be a lot more stuff like that where latency is really important. So also, latency is really important. Things like gaming, virtual reality, augmented reality, and all those are still fairly primitive technologies. I know gaming is very sophisticated, but gaming as a service where you can deliver a full gaming experience without the need to have a console is still in its real infancy. And that really needs edge infrastructure to make that real. So that's one thing. That data processing is the sort of other main benefit of using edge, because A lot of the sort of new applications now rely on huge amounts of video data being processed, analyzed, and the amount of data that can be generated in a single site. I'll give you an example. In retail stores that have, the sort of pick and go type facilities. So you walk into a shop, you swipe your credit card, then you just go in, take stuff, move it, and go out. You don't scan, you don't do anything else, you don't check out, you just take stuff and go. Now that works by using possibly hundreds of cameras within a single retail environment and then analyzing it and boiling that data down to a very small number of transactions, which ends up as, a debit on your credit card. Now, shipping that data to a remote data center would be prohibitively expensive because the sheer volume of data that gets generated is enormous. But actually, the useful data is a tiny, tiny fraction of what's actually been generated. So the best thing to do is to process it nearby so that you don't have to transmit that data halfway around the world or, to Sweden or wherever. It's just much, much more efficient and in many cases, the only economically viable way of doing things. So the edge, that we're going to see, it's not just retail. There are all sorts of different applications for this, but it'll be latency, it'll be data processing, and finally a sort of data security. By being able to keep all the data and the processing nearby, it gives you much greater control for security, for resilience, for just general compliance with local regulations as well. So there are lots of things that are driving companies towards using the edge more and more, and we're now beginning to see infrastructure being built out to support it. And it's I think going to be one of the most exciting areas in sort of our industry for the next few years. It's again, a lot of it's driven by AI. So the AI sort of inference which happens at the edge, that those platforms are what we need to start deploying. And we think the usage is just going to escalate, like I say, probably exponentially for some time to come.
Duncan Clubb, thank you very much indeed for joining us.
Thank you.
Thanks again to Duncan Clubb. In our last episode, we heard how materials science is taking us on an innovation journey to new types of compute promising improved performance and efficiency. And our next guest today, Mihai Raneti from CyberSwarm, continues that compute innovation journey, albeit down a slightly different path.
I'm Mihai Raneti. I'm CEO and founder of CyberSwarm. We are developing a new type of chip architecture, an architecture which works in a similar way to a biological brain. Basically mimics the functionalities of a biological brain. And by doing this, we are achieving a low power consumption mode, while also enabling our hardware the capability to learn by itself without internet connection.
What are the main sort of features then that we get, the main benefits, if you like, from having a processing unit, a chip as you call it, that's closer to a biological brain than what we've developed over the last 70 or 80 years?
There are some very deep differences. The current architecture was envisioned by von Neumann in the 1940s. So basically the process of process data in the sense that it moves a lot of data from one place to another. In order to do that, we need a large number of transistors. We are using a lot of power for that. And the processing unit itself does not think, only transfer data from, let's say, from our hard disk to the RAM and vice versa. And in this situation, the thinking is being done by the software, which is on top of everything, right? In nature, in biology, everything is in the same spot, right? In our brains, as an example, we have the storage, we have the computing, and we have the random access memory. And because you have that, the power consumption is very low. Obviously, the brain has the capability of learning by itself. We don't need internet connection to download that or do lots of other things, so we can achieve that by learning. AI systems, AI software systems such as large language models and deep neural networks, they do consume a lot of power because the underlying hardware is built in such a way in which, okay, you need to move lots of data from one thing to another, right? And the power consumption is actually quite huge. And as a matter of fact, a simple ChatGPT query, it's actually 50 times more expensive than a single Google query for that. And this is why what we are doing paves the way towards an artificial brain, which can be perceived as both a novel type of chip of computing actually, and at the same time enables practically will enable new forms of AI, because on our chip the software doesn't exist. Everything happens only by using nature's law, electric power laws, and that's it. Again, just like in a biological brain.
So a lot of energy is wasted in moving around information unnecessarily. And so by keeping stuff, the processing and the memory, the storage in the same place, there's a lot more efficiency to be had there. Like you say, very much like how organic brains, organic systems operate. And another benefit of this type of application here is that these systems are able, are they not, to learn essentially by themselves without necessarily needing an external connection, an internet connection, for example. What are the kind of applications that you see this having on this planet and perhaps beyond?
I'm going to refer about the automotive case. It's very hard to achieve full self-driving capabilities for any kind of car, mainly because neural networks have an inference latency of around 50 milliseconds. And that's quite slow. And that means that if you are going to use neural networks, which are developed and used in software, on the software side, you're not going to have enough time to recognize the object and to take the action to avoid that obstacle or not, right? But because in our situation everything happens at the hardware level, the inference speed is basically close to the speed of light, right? So basically it's below 1 millisecond. And in that situation, you can achieve full self-driving car, right? For self-driving capabilities. That's one of the use cases we are deployed. That's one of the use cases we are doing right now for one automotive manufacturer. The second situation is going to be on the moon surface. On the moon, we do not have internet. And we are going to have astronauts there and no internet connection, right? And let's say they are going to have this kind of small rover, and that you'd like to have that rover the capability of avoiding certain rocks, obstacles there, but you don't have internet. So in that situation, you can send this kind of rover, which will learn by itself how to avoid certain things, right? It will be able to recognize several things, and it will avoid that without internet connection. And these are the most important use cases we are working right now.
It does seem like a very different paradigm to the compute that we've been used to, that was grown up around us over the last few decades. Where are we now with the development, but also the deployment of this neuromorphic technology?
We are deploying it right now within the automotive industry. Of course, we are pursuing the silicon path because it's a little bit easier to integrate right now. But I think that in the future, the glass chips might be far more interesting, mainly because their developing and manufacturing costs should be extremely low. Long story short, the silicon wafer is pretty small, but imagine that a display factory manufacturing displays for laptops, for TVs, can manufacture this kind of chips on a larger scale, and this means we are going to have cheaper chips. Right now we are implementing it within the industry. We have several other projects coming soon.
These devices seem to be like the ultimate edge devices, if you like. Where do you see these sitting alongside some of the more traditional centralized compute cloud data center type applications of technology?
I think they're going to complement each other because right now in a data center, we already get lots of data, and we are analyzing that data from a statistical point of view. So when a mobile phone recognizes a shape, it doesn't recognize by itself. Basically, some kind of algorithm within a data center recognizes that, right? But I think that in the future, everything on basically on the edge, I mean humanoid robots, sensors, and this kind of healthcare devices and equipments, they are going to be able to process and to make those decisions locally without needing this kind of internet connection to and from a data center. And this way we'll have some form of autonomy, and it'll allow us to develop basically a lot of applications and a lot of algorithms on the edge, which we cannot really do that right now.
What are you most excited about by this technology that you are developing?
I think that what we are developing will democratize AI for everyone. And I think that, initially when the electrical power is being generated by those two guys, Thomas Edison and Nikola Tesla, right? There were only a few companies in the world able to generate that electric power. And after a while, lots of other companies used that. It happened in internet. Some guy invented that, some like this. And I think that this kind of hardware will enable a personal AI, I think, for everyone.
Wow, really interesting stuff there from Mihai Raneti from CyberSwarm. Vipul is still with us here in the studio. What did you make of that? I know that you've been doing some work with Mihai and CyberSwarm. It's a completely different way of thinking almost, but it really speaks to that point about the edge and the benefits that these edge computing models can bring.
100%, David. Technology has moved a lot. And let's agree to that, because what was relevant 30 years back is not even relevant anymore in terms of technology, in terms of the network which is connected to, the fast network which enables us to do a lot of things that it used to. The perimeters of our infrastructure and our technology footprint have expanded exponentially. What does that mean? Power consumption, which we have heard about in the past. We're talking about AI, boom, major AI. Algorithms, user cases, trainings, LLMs. How does it all fit together? Imagine a situation where you have got a chip which can have hundreds of thousands of algorithms on a single chip. Ability to take decisions at a speed of light. Neuromorphic capability. Mimics our brain. How faster do we think? How faster do we think that a car is in front of us and we have to put the brakes on? That is how fast we are talking about. The inability to consume power at 1 to 5 volts, which is 1 to 100 times smaller than any average size GPU. It changes the equation for edge compute. It changes the equation on how we see cars of the future.
Yeah.
We see robotics, we see drones, we see every IoT infrastructure consuming that and creating the right kind of data source or the right kind of user case which works for them, whether it's manufacturing, retail, or as I said, in pharma and the other parts of the business.
We've been talking about hyperconnectivity, Internet of Things for quite a while now, and it seems to me as though one of the barriers that's still there is, going back to an earlier episode in the series, that thing of power. Because yes, we could connect all manner of devices around us, more than already are connected, but if I'm having to go around and change the battery in them every year, then I'm afraid it's just not going to happen. So surely some of those barriers about power, about these devices being maybe self-powering, that's the hill that we need to climb and see over the top of before we can really start to feel the benefit of this, again, as individuals, but also as cities, smart cities, about Industry 4.0, Industry 5.0 maybe.
Yes. And imagine these devices on every single IoT, the devices on our phone, devices on the infrastructure. We're talking to robots, basically, of the future. That is what will change. And that is how these devices, on neuromorphic capability, I would say in general, if you look at Gartner and you will look at the top brands of future, one of the key areas they are saying, one of the 10 technology initiatives is neuromorphic. So yes, it's going to change the world. It's going to bring in the actual intelligence in the AI field. So it's going to transform a lot of what we're seeing today, and a lot is what is going to happen in the next 10 years of innovation. And we are happy that we are in the middle of this innovation boom, and we are actively participating in testing, creating, and innovating.
And one of the first sort of areas where we might, as consumers, start to see some of the benefits, the impacts of this are in these, I guess, autonomous devices, whether that's drones, autonomously flying, making decisions on the fly, literally, or in autonomous vehicles. Something that's been promised for a very long time, but haven't up until now really delivered. That barrier has been the split second, the split millisecond decision making. That's what edge computing, as we've been talking about it today, really brings. With great power comes great responsibility.
Yes, I'm a big fan of that. My daughter is. With great powers comes great responsibility. And it's amazingly true.
Yeah.
Because as you start moving into this area, you're talking about data, you're talking about large language models, you're talking about exposing yourself to both good actors and the bad actors. And we need to remember one thing, David, and we need to agree with that as well, that we have to protect 100% of the time, be successful protecting. And the bad actors have to be successful once to break the bone. So and that is what we have to protect. And this is where, with the neuromorphic capability, it gives us the ability or challenge or opportunity to have the right security barriers, the right security guardrails which protect us from the good actors versus the bad actors, and let the AI also run in a smooth way to make sure that they're taking the right decisions.
And by right decisions there, you mentioned guardrails. It's easy, well, it's not easy to talk about privacy. It's not easy to talk about security. But the other thing that it's also not easy to talk about in this domain is ethics as well, having some guardrails. Just because AI can do something, maybe it can do it with privacy and it can do it with security, but should it be doing it? Who makes those decisions? Who controls what the AI is allowed to do?
It's an amazingly important question. And right now there, as I said, a lot of people are thinking about it. What should we give AI control of? AI should be given enough control to manage a specific user case where it's applicable. Yes, there can be questions about if you don't give AI full autonomy, then how can it function? Yes, but there are certain areas where they don't need to have full autonomy. There has to be the human factor in. I'll give an example. The East and West divide, what we call in AI, where things which are applicable in the East are not applicable in the West, and vice versa. The mortgage capabilities, which are the mortgage decisions now taken by AI to give a mortgage to a family of 2 and 3 or 4 small families, the decisions in the West cannot be implemented in the East unless there's a human factor in. The way they create their livestock is not something which we would give control to an AI to make a decision whether we give you a loan or for creating your home or not. A lot of people globally, a lot of forums are talking about this on a daily basis. How to bring in the human factor, how to make sure that AI is ethical AI. How do we make sure that we are putting the right guardrails? Who is controlling them? A lot of new standards, 42001 has just come out, which talks about AI and how the guardrails need to be implemented. But there are countries, there are places where even though you won't let to implement those guardrails. So we need to be aware that we are fully agnostic, or we should be fully agnostic of what AI methodology or guardrails, whether it's DeepSeek you're working on, whether it's Gemini or whether it's ChatGPT, whichever models you use, the idea is to make sure that they are secure, boundary after boundary after boundary. And that comes with a lot of, again, we started talking about neuromorphic AI, but that spills into every single area. even hardware-based security based on binary codes, which are based on impulses and pulses.
What you've really done for me in this chat, Vipul, is to draw this line between edge, what edge is, of course, and we've learned that in all the conversations today, but really draw that line between edge and AI, and that really AI is kind of the killer app, if you like, for what edge is and what edge brings. And they can't really coexist in some of these more autonomous modes that we're talking about with vehicles, with drones, with other types of decision making in the moment. They can't really exist without one another. And that's a fascinating insight. I've really learned something today. Thank you for that.
Thank you.
In the next episode, we are going to be taking, we've had a bit of a cybersecurity sidebar. It's going to be the main bar in our next episode, because innovation doesn't only have a positive impact on society. Bad actors are busy innovating too in order to achieve, whatever their goals may be. That's coming up in episode 5 of Impactful Innovation with Commercis. Hope you can join us. But until then, bye-bye.